This lecture, the beginning, will be the most difficult part. When we get about halfway through, it should get a lot more understandable. This is probably the most difficult bit of the whole 10 lectures, this first half of this. So because we're going to a higher level, we're going to beyond quantum mechanics towards quantum field theory. And it's a higher level of complexity. But we have to show that we can do it. That's the main reason for doing this, to show that we can do it. So some of these calculations are going to be a bit more involved, but we'll not dwell on them. And I've already mentioned that there's quite a bit of quantum field theory already in the nilpotent quantum mechanics. The nilpotent wave function are already the result of creation and annihilation operators acting in a vacuum state. So they're already coming, ready, set and quantized. If you want the mathematical proof of that, you need to turn to 0 to infinity. Renormalization, in the sense that you rescale your electric field, your electric coupling constants, your mass and so forth, as you go along for interactions, should still apply. But what we hope to eliminate is the need for the infinite self-energy term, which causes the problem. Because there are two aspects to renormalization. There's one that rescales everything, and there's another one where you get this infinite term and you don't know what to do with it. Except find some mathematical trickery to eliminate it. So we hope to get rid of that. If we expect the nilpotent formalisms just from the symmetries of nature, well, then we don't expect to find these things as a fundamental aspect of nature. That we expect them to be an artifact of the mathematical structures we use. Now, we already have an exact supersymmetry. We were talking about that in lecture 6. And as a consequence of it being nilpotent and representing vacuum as well as Fermion state. So we would expect that if we had to do a quantum field calculation, we would get the loop cancellations we need to avoid this infinite self-energy term. We'd expect free fermion and the boson loops, which we can describe with using the same structure, to be an exact cancellation and to avoid the hierarchy problem. So this is how we would begin quantum field theory, quantum electrodynamics. Now, of course, nowadays, you'd go straight into the Feynman formalism. You'd go straight, draw the Feynman diagram and use the Feynman rules to do it. But the Feynman rules were based on more fundamental processes, and this was typical of the kind of process. If you start off with a standard Dirac equation involving electric field terms, so this is the energy term and this is the scalar potential term. So that's the scalar potential energy for the electric force. That's a vector potential term for the electric force. So this is how the equation would look if you included those terms. And just rearranging the equation, you would get that. Now, what perturbation expansion would do is to say that we can make the real wave function out of the first go at the wave function, then plus a series of iterative bits we added on as we proceeded through the calculation. And so the first term would look like that. That would be the solution of the unperturbed equation, psi naught. So that would be the first go we get without any electric field.
So just to be precise, this is exactly the normal.
Completely normal, yes. Nothing original in this. We would eventually go through a lot of terms like that, psi 1, psi 2, and so on forever. Now, the psi naught, if we use psi naught, we would get equals naught. When we use psi 1, what we do is go to this equation, this one here, and put psi naught on this side and psi 1 on this side. So that's the first one. And then it will become psi 2 and psi 1. This is completely standard, so I don't want to dwell on that. And we could eventually start developing the perturbation series. And one of the techniques used is to then expand expanding the field terms as a Fourier series over a momentum. So that's how we would expand the field terms over a momentum. I don't know what that is, that's just crept into the representation. And we would get something like that. We would eventually start building up a series. So we carry on expanding this, and we would come up with something like that. And then we would have equate individual terms, and we would get expressions like that, which I don't really want to do too much about. What I'm interested in, though, is that we would eventually get something that would represent a wave function for first order coupling, the psi1. We would come up with something of that kind. And that's a fairly standard, but it's written in nilpotent form. If you got it in a standard book, it would look like that, but it wouldn't have the K's and the J's in. And that would represent a first order coupling with a fermion absorbing a photon of momentum K. If we now say that what I want to do, so what I'm showing there is that one can simply use this mathematics in the standard way. Nothing original there, but one has to show one can do it, so one can do it. However, what I'm interested in here is a possible way of looking at the self-energy term. And if we said that if we get rid of the external source of potential and only look at the internal source of potential, an internal source of potential, let's suppose that we reduce the internal source, the whole potential just to an internal one, which we'd still write in this form, but it would be an internal one.
Now, what is internal?
Self-interacting. So we've got no external K, so we've got no photon external, it's only the internal potential. So it's not interacting with another system, it's only with itself. And then I would say, let's take it in the rest frame, so let's remove the vector potential and make it all scalar potential, which we can do. We can write it in that frame. Then the first order term would look like that. The thing that is interesting here is if one works out this term, what it looks like this. And this means that if one has only self-interaction, according to this way of looking at it, one ends up with this. And because this is nilpotent, this actually zeros. So we actually lose our first order self-interaction term. And therefore the second order, the third order, and the fourth order to infinity. So that's an indication that we can possibly get rid of this self-energy term. I'm not saying it's a proof, it's an indication. If this is correct, then we should be able to do the same thing using the loops argument, which is a better way of doing it. And it's what we'd expect from this system. The total energy is zero, and we should be able to combine negative energy fermions with positive energy bosons in the loop structures. That's the way they work in the loop structures. So in the nilpotent, every fermionic state has intrinsic supersymmetry, spin one bosonic partner. If we've got a spin half fermion, that's what it looks like. This is a spin half antifermion. And we've seen that these are each unchanged if we post-multiply by an expression like that. So if we post-multiply by those expressions, then this is simply this. We can post-multiply as many times as we want, and it won't change. And the same with that one. And of course, now we can take the k from that, and multiply them, and change the k term there to a negative. But this one will stay positive, but the next one will be negative, which of course creates the boson loops. And the same with the antifermion. So we're alternating spin half and spin half minus half fermions with spin 1 and spin minus 1 bosons. So the fermion is generating its own vacuum boson partner, and they've got the same energy, momentum and mass. Now, can we actually do that? Well, I say yes, we can. And in fact, we can reduce it to arithmetic. Of course, most of the work's already done for us because most of the work is done by the quantum field theorists. And we can just take their equations, and so we show we can input that, and we get zero for our totals. This is a typical quantum field theory expression for the vacuum energy for a particle of mass m and spin j. It would look like that. And the logarithmic, quartic, quadratic divergences are all this stuff over here. To remove those, what we need is that spin to get that summation to zero, to get that summation to zero, get that summation to zero, and then every multiple afterwards to infinity to zero.
This is standard.
The complete standard. I've not done anything original there. Now we've got J's plus or minus half for the fermions loops and plus or minus 1 for the boson loops. So let's add them together. And these are what we get. For J's a half and J's minus half, we get those. For J's 1 and J's minus 1, we get those. Add them together, we get 0, which is what we want. I don't think I'm saying anything that hasn't been said before, except that we can now do it.
Right, 2J plus 1.
Yeah, but I've not done that one yet.
So on the next page, you've got 2J plus 1 to the 2J.
Yeah, I'm sorry, I've probably copied it wrongly there. That's probably wrong, actually. Now, if we got equal masses for the fermions and bosons, which we have, then we don't need to worry about the mass term, because those will also operate as well. Those will also operate as well, because the mass will be the same for each. If the masses, the fermions and bosons were different, we couldn't do that summation. But we can, it's the same mass. So we can do that one as well, and that one, and all the rest of them to infinity. This is only what the standard theory says, except that what I'm saying is that in this particular formalism, bosons and fermions look the same. And if you've got a fermion, you've also got a boson. And if you've got a boson, you've also got fermions. And you can do the same with your bosons as well. And I don't think there is any hierarchy problem whatsoever. And in fact, one can do it just using arithmetic. Once you realise what you've got, there's no difficulty in the calculation at all. It becomes just arithmetic. I'm just saying you can do it with the bosons as well, the other way around. It's just explaining how you do it with them. I'm saying that there's another argument that's of interest here. This is another problem that people talk about, matter-antimatter asymmetry, and they go to cosmology to explain it. I don't think it's anything to do with cosmology. Matter and antimatter asymmetry has nothing whatsoever to do with cosmology in my view. You've got more fermions than you've got antifermions. It's said that equal amounts of fermions and antifermions are created in the Big Bang, with the fermions slightly in excess. Following this mysterious process, which is called baryogenesis, removes most of the antifermions and just leaves a few fermions. That's what people say. But I say you don't need to look at it that way at all. The asymmetry could just as well be generic, and in fact it's not an asymmetry. When you write down that Dirac wave function, you write down 2 fermions and 2 antifermions. The wave function includes the same number of fermions and antifermions. If you add it together, it's nothing. And what we're saying is that we've got 2 spaces. One we call real space, because that's what we observe, and one we call vacuum space, which is the space we don't observe. The fermions are in the real space and the antifermions are in the vacuum space. They're still the same number. The same number in nature, they're just in different spaces. And only one space is the one we observe. But we know the others exist. We know it has to exist. So there aren't any more fermions than antifermions. I'm saying it's not a problem that there's an asymmetry, because there isn't an asymmetry if you look at it that way.
Well, that means the C operator takes you from one space to another.
Correct. Yeah. So, but we need both spaces to explain physics. It's just that we observe one and we don't observe the other. I don't think there is a problem. So E is the fermions, characteristic particle defining real observable antifermions, define vacuum space. So there's no asymmetry at all. And in the nilpotent structure, we've got 2 energies, plus and minus, just as we have, 2 directions of time, 2 directions of spin, 2 fermions and 2 antifermions. There's even 2 causalities, because your non-local structures have backward causality. That's one of the problems of quantum mechanics, that you've got backward causality in effect, reverse causality in quantum mechanics. It's future, not past, that you're looking at in quantum mechanics with your non-local bit, your vacuum. The vacuum gives you your future. So you've got backward or reverse causality for non-local vacuum. All the future causes of anything that's going to happen are in that vacuum. The only thing that only ever has positive value is mass, but then mass isn't a fundamental property in this. It simply emerges by switching between the 2 spaces. Opposite of a vacuum. I just want to say a little bit about propagators. I don't really want to go into too much detail. What I want to say about this is that these are objects that are used a lot in particle physics, and these have another singularity problem. Again, it's because we've got two dual vector spaces. The Zitterbewegung is switching between them, equivalent to switching between positive and negative energy. And the Feynman formalism for the propagators produces a pole or singularity at exactly the division of switchover. So when you switch from electron to anti-electron, that's where you get the pole. And that causes the problems. You've got positive energies in one, negative energies in the other, positive times, negative times. And you get a divergence at that point. Now, it's normal to use a mathematical trick to avoid it, but if we're using a mathematical trick to avoid it, perhaps we don't need to structure our mathematics to include it. There is a pole, but we don't need to actually look at it nakedly. This P slash is basically gamma mu d mu. It's the differential operator with four terms, space and time. So this is a typical Fermion propagator. There's just 1 over P slash minus m. In other words, basically one of the differential operators. And if you multiply it by P slash plus m, you get P squared minus m squared. And of course, if you get P squared equals m squared, so all the energy and momentum terms become equal to the mass term, and the pole, then you get an infinity, a singularity. And this is what the subterfuge used is. You add a plus I epsilon term to this. So you add a term with an imaginary term to it. And then you do a contour integral, and you do it over the two different times. That's the positive time or the negative time. That you switch. That's the positive time. That's the negative time. Positive energy, negative energy. You do a summation over it, and then that's the two spin states for it, and that's the two spin states for that one. And so that's the usual way of dealing with it. But I say, let's now have a look at how we would do it. Our operator would look like that. When we actually multiply it by one of its complex conjugates, we don't get a term that can ever be negative. It becomes a positive scalar, always just a scalar. So we don't get the singularity because of the way we've structured the equation. It's finite at all values. If we write the integral, we just have one term like that because we've collected all our terms into one structure with one phase, and our positive and negative energy solutions are collected into one. So we get an object looking like that, a single object. So we get a single package with the negative energy states already matched to the positive energy states. There's no averaging over spin states, no separation of positive and negative energy. It's one structure, one package. There's no division between particle and antiparticle. The two come together as one unit. And that's simply an artifact of mathematics, whereas in the previous mathematics, they were separated. If we derive a boson propagator, and we derive that from the Klein-Gordon equation, we end up with, of course its mathematical form depends on the gauge, but we won't go into that. If we take the Klein-Gordon operator, it looks like that. It's the only scalar product you can get from a linear differential operator, defined in this way. However, I say we shouldn't define our boson propagators that way, we should define them that way. There's three different ones depending on which boson we've got. So we get one for spin 1, which looks like that, one for spin 0, which looks like that, and one for the paired fermion states, which looks like that. And they're all non-zero at all times. I say you've got the relationship between the fermion and boson propagators is, as we would expect, it's the nilpotent structure. Exactly the same as we get between fermions and bosons. And then when we do a contour integral, if we did one, we would get something looking like that, a single expression, and no singularity at all. I mean, the main problem with these is that when E squared equals P squared plus M squared, you can get rid of it when it's not equal to that, but when it is equal to that, in those particular cases of massless bosons, then you can't prevent an infrared divergence, but we don't get one. There simply isn't one. There's no naked pole in the expression. We know there's a pole because there's a particle, but there's no naked pole. I think it's just an artifact of the mathematical structure. We ought to be able to devise a mathematical structure which gets rid of it. That's so much for that. Let's just try something else let's see if we can do standard calculations using this. And I'm not going to do anything that's different in result, but I'm going to do something that looks different. This is how one would got the p/ notation still, and this is how one would do mu on decay using using the Fermi approximation, which is the 4-point Fermi interaction.
Right.
You get an invariant amplitude looking like that. I only wrote that down first. That's the trace theorems I used to do that. And the spin average probability looks like that. So I'm actually using the standard theory. And this is your Feynman diagram for it. All I'm saying is how I would approach that mathematically. Would be no different physics, no different. It would simply be like that. That's how I would do it. I start off by doing a few identities and things. That's what a few identities I need. And then we've got p/1 is that, because I'm treating these as operators now. And if we could even include a mass term if we want, which we don't normally do in the muon decay calculation. And then if I write down now, I get that. So if I use all those, I will eventually get to that, which is 16 of those. And 2 of them together is going to be 256, as in the standard version. So I'm going to get exactly the same as the standard calculation, but I've just done it differently. What I'm doing is getting rid of the trace theorems. So I'm just doing the mathematics differently. Physics is exactly the same, so I've included all the physics. What I would like to do eventually is to do a lot more standard calculations, or get other people to do standard calculations, so we can build up a portfolio of these for general use. Because I think my method's easier than the standard one, as it happens. Because you just multiply everything out, and you don't have to know lots of special mathematics to do it. This is another aspect of quantum field theory. And I think Mike first mentioned this possibility to me that I should look at BRST quantization. It's named after 4 people. So if we look at 1 or 2 more conventional approaches, this is quite an interesting one. In standard theory, field quantization requires gauge fixing, so you've got to remove gauge invariance to do the field quantization before you can construct the propagators. Standard quantization uses Coulomb gauge, but that means you lose your Lorentz invariance. Now, if you use the path integral approach, we can use any gauge, and so we can maintain our Lorentz invariance. But now we have another problem. We get non-physical, fictitious ghost fields, Fadde F pop-up. There's a version called BRST, which eliminates the ghost fields, and it packages all the information into a single operator, which you apply to the Lagrangian. And interesting, that's a nilpotent. BRST operators are nilpotent. And then you can construct a Noether current corresponding to the BRST conserved fermionic charge. And you get this condition, so this is the conserved charge, you get this condition, QBRST, and on the operator on the wave function is 0. Now, if we look at the Dirac formulation that we've used, it's already second quantized, and it's already a nilpotent operator of that form. It's also a nilpotent charge operator, but extended to beyond electric charge to include strong and weak charges as well. And then finally, in its eigenvalue form, it's identical to that. So all 3 possible meanings of that apply respectively. So if one looks at this particular standard version of quantum field theory, then we can show that if we use the nilpotent structure that we have from this, we can use it to do all 3 jobs together. That separately does. Okay, I want to go on to mass generation. As we know that if we're going to have a massless fermions, we require either pure weak interaction, we require left-handed fermions and right-handed antifermions. And so I want just to have some principle of how this might work to involve something like Higgs mechanism. So let's imagine a fermion vacuum with 0 mass for a fermion, and it will have a wave function without a mass, let's say something like that. So if it's an ideal vacuum, it should have exact absolute CP and T symmetries. Under C transformation, it will become like that, and with which it's indistinguishable. You can't tell the difference. Now, suppose the vacuum's degenerate. Suppose that you've got that state, and that state is degenerate. It isn't the same. Then if it's degenerate, then you need a transfer mechanism. If you're transferring from one fermionic state to another, you need a bosonic state to transfer. Now, that actually cannot exist in this theory because it's zero. It's spin zero, that's a spin zero state, but it must have a mass. So you cannot actually create that state. If you've got a vacuum that's degenerate and looks like that, without mass, then it has to have a mass, because otherwise it can't exist, because it will zero immediately, because that's nilpotent. If the degree of left-handed helicity is determined by this, because that's one helicity is one sine of this IP over IKE, and the other one is the other sine, then if you will change this ratio, if this ratio is what determines the helicity, how much left-handed it is, then if we change that ratio, if we have a mass term, we will change that ratio. And we will add right-handedness if it's left-handed. If it's left-handed, we'll add, if it's right-handed, we'll add left-handedness. I'm actually looking at the way one would look, why you cannot have a spin zero boson without mass. You cannot. Now that is not in Dirac formalism. So only part of it is in Dirac formalism. I think I will not do that. Let's mention something about string theory. What I'm interested in string theory, I'm not really interested in the strings particularly. What I'm interested in is the 10 dimensions and other fundamental things. Because this is basically a symmetry argument which says that 10 dimensions are needed to remove various anomalies from physics. And then they have the problem, how do you reduce 10 to 4? In that we see, so they say that the other 6 must be compactified. And then you've got the hosepipe analogy, and what you get is, if you have a hosepipe, basically if you create a circle structure, you are really, in some form, creating a U1 symmetry, because that's how the U1 symmetry is defined. And it automatically creates a U1 structure if you compactify in that form. And standard string theory connects that with Kaluza-Klein theory, which interestingly are two different theories, they're not the same theory. Kaluza-Klein theory added a 5th dimension to general relativity. I'm not sure who did what, but one of them did it to show how charge was created, electric charge, and the other one did it to show how inertial mass was created, rest mass. So there were two different theories with a 5th dimension that each did one of those. And certainly, if string theory is talking about below the Planck length, then you're not really talking necessarily about spatial or temporal dimensions as we know them. Now, I say that string theory was never intended to be a model-dependent theory. String theorists will tell you that is only a route to actually getting something more abstract. So why don't we have a look, see if we can get something more abstract which has the required properties. The object is to find the correct vacuum, which will generate the compactification. And many possible string theories, 5 types. Membrane theory proposes that the different types can be combined if an extra dimension is added. So this is standard string theory. So the objects of M theory are 2-dimensional objects in 1-dimensional time, which is why that ends up with 11 dimensions, as opposed to string theory, which has 1-dimensional objects in 1-dimensional time. Now this combination is talked about, but it's never actually happened. There's only an indication that it might. We're not interested in here in producing a new string theory, but we're interested in the significance of 10 dimensions. So how would we look at that? Well, I say the nilpotent operator here is 10-dimensional. It can be seen as a 10-dimensional object. This is something I noticed very early on with it. If you have 5 dimensions here, well, energy, momentum, mass, but you also have 5 dimensions of charge. You have a total of 10 dimensions in that structure. You've got 2 spaces, 5 dimensions and 5 dimensions, 10 dimensions. And that's why it can happen, because you've got fundamental duality between two spaces. Each of the spaces is only 3 dimensions, but by combining it, you make each of them 5 because of the way you do it. And as I mentioned earlier, Clifford algebra can do these tricks. And actually 6 of those are compactified because 6 of them are fixed. There's only the energy and momentum ones that aren't. The charge ones are, and the mass one is. So there are 6 that are compactified. And it is also double 5-dimensional, which is very close to what Kaluza-Klein theory says. And the 5th dimension in this one, if we go back, is in fact this one, which is either the mass or the electric charge one. J has always been the electric charge in this formalism. So we got some interesting analogies here. Let's look at what John Byers, a well-known theorist, talks about. Very interesting theorist with lots of original ideas. He thinks that the 10 dimensions indicate the existence of 2-dimensional strings in an 8-dimensional space, which could be octonian. And then he suggests octonian space is the true basis of physics. Well, we have a broken octonian here. Clifford algebra can do this, as I mentioned, can do these things. We can also say this is an 8-dimensional object. Why is it an 8-dimensional object? Because this dimension here, these 2 dimensions, are redundant in total because it squares to 0. So it's 10-dimensional or 8-dimensional, depending on how you think of it. The whole structure originates in the combination of the 4 dimensions of space and time and the 4 of mass and charge. So we have 8 fundamental dimensions, a broken octonian, and you put them together and it creates a 10-dimensional structure. You could also look at it saying that the fermionic object is a 3-dimensional structure in Ki and J. And it's point-like in space with one of the 3 dimensions redundant because you only need 2 of them to find the other one. In string theory or membrane theory, you would have some object which created a structure that combined these 2. Here you've got a point, and that's why it reduces to 0 and makes one of them or 2 of them redundant. Now, one of our colleagues here has a formula for what perfect string theory should be. I've never asked him what he means by this, but it would be interesting to talk about it. Alan Faraggi says, self-duality in phase space determines vacuum selection, and that's perfect string theory. Very interested in that because the nilpotent structure we have is that it is self-dual without a doubt. It is phase space, energy, momentum, mass, and it also determines its own vacuum because its negative is its vacuum, it's multiplied by its vacuum, it's 0. So whether he means that or not, I don't know, but it certainly does do that. Other things that interest me in string theory, I remember Michael Green talking about the first one, gravity gauge theory correspondence, in which gravity and gauge theory are like 2 dual things. Gravity and gauge theory contain the same information. Gauge theory, the other 3 interactions. And I have always been finding that gravity and gauge theory are kind of like symmetric opposites. Another one is the holographic principle. The holographic principle says that all the information about any state, any system is on the bounding area. So you've got all the information about a system in the area. And what do you mean by the area? You mean either space by space or time by time, or space by time. And if we look at our structure here, this term is effectively redundant because it squares to 0. And this acts like the bounding area. I can do that in more detail at another time. I don't want to talk about it too much today. It's very interesting to look at it in this term. We can look at this and say that a lot of the things that string theory is interested in, I am also interested in. And maybe they are looking at it from a related point of view because many of the symmetries look very related. Now this is a picture that interests me. This is by John Wheeler, and the only reference to it in the literature, he was in Feynman's Nobel Prize lecture. He talked about the Wheeler one electron theory of the universe, which, because An electron in going backwards in time is the same as an anti-electron. You could eventually make all the electrons and all the fermions, as we can now extend it to a one fermion theory, all the fermions in the universe into one fermion in different space and time states. Now there were a couple of objections against the one fermion theory in the past, that it would require equal number of fermions and antifermions, and we didn't see that, and that they would annihilate if they existed. Now, of course, in the explanation I've given, we do have equal numbers of fermions and antifermions, and also they won't annihilate because they're in different spaces. The objections that have been raised against that interpretation, it's not a theory, it's just an interpretation, a way of looking at it, seems to be invalid, and I think this is a perfectly good interpretation. It's at least as good as the multiverse type interpretation. So an ensemble won't be localized as narrowly as a single fermion, so its vacuum won't be as non-local, but you can treat it as one. Now if we take the whole universe to be a fermion, we can imagine all the space and time conditions, and this man Seth Lloyd used the expression bit flips for all the possible quantum transitions and all that, as constituting this universe which we call vacuum. So this includes all the states which the fermion could become over time. So that's why it's got forward causality. That gives it forward causality, which is what we mentioned earlier. So a single fermion includes the entire possible history of the universe within its event horizon. I should have said backward causality, I'm not sure which is which, but the opposite to normal causality. That would make sense of thermodynamics as a unique birth ordering. However, it's not deterministic, because to make it deterministic, we'd have to localize the fermion exactly, and we know that we can't do that. So we can localize in time or in space. Now I want to talk a bit about dualities generally. So we've got fundamental dualities, which are intrinsic components of the structure here. Operator and wave function, standard duality. Fermion and vacuum comes from the principle if you define a fermion state, you're defining a fundamental singularity. And if we define a singularity, we need to define what isn't singular. So we can view the fermion as a singularity with connections leading out. The vacuum acts as a kind of inverse singularity, with the connections coming into the singularity. You can see it that way, source and sink if you want. This duality says vacuum isn't something separated from the fermion. We can't define the fermion without defining it, and the spinor structure. And this is why the fermion has half-integral spin, because we can only define it by simultaneously splitting the universe into two halves, which are mirror images. And this, of course, relates to our other model of the quantum mechanics, the multiverse one, the multi-universe one. The duality manifests itself physically in zeta Bavagon. Yeah, if we use the convention that we use, the first state is the actual state at any one moment, and the rest of the states are dimensions of vacuum into which it could transform if we used a P, T or C transformation. So the duality makes sure that fermion and vacuum are separate three-dimensional spaces. These spaces, though seemingly different, though, are still dual. The same information is in each. Even though one is accessible and the other isn't, it's the same information. We've got many different forms. Let me show you some of the forms in which this duality occurs. If we have Pauli exclusion, so you've got blue ones and red ones. This is ordinary space, and this is vacuum space. And if we do Pauli exclusion by antisymmetric wave functions, we use ordinary space. P cross P, P1 cross P, P2. If we use nilpotency, we're using the red space, the IKJ quaternions. If we use angular momentum again, it's these three in this space, or it's those three in that space. It's the same information, just differently organised. Spin half, we make P anticommutative. Or we do the Thomas precession, the first way it was done, which is like anything to do with relativity, is really vacuum space. Special relativity velocity addition. Now I've seen this done. I've seen it done using two space components, which is quite amazing, but it can be done. A man did it with using two rulers moving about, and it was quite convincing. Or we use the normal space and time. Or we can do the holographic pinch principle, which is space and space, or the area can be done as space and time. So, if you like, we've got two different spaces, two different structures, but we've got the same information, differently organised. And I sometimes call this one the anti-space because, of course, it's a totality zero. If we talk about Pauli exclusion, we can use those three or those on orthogonal axes, and each will give a vector that's unique, and that's the total information about the system. And the information that it's giving is the angular momentum, which contains all the information. When you have a quantum transition, it's a transition of angular momentum, h. That's what it's all about. There are three separate pieces of information that you need for angular momentum, magnitude, direct. This is provided when we use those. It's also provided when we include all the information on the p vector alone. I think I've already talked about that one. So this is simply saying that we can use either the spin half by that method or by that method. And in fact, there are other methods, but those two methods use different spaces. And I've just mentioned about the velocity addition law. I've got a paper written by this individual about that, and it's very interesting. So in all these examples, we need two vector spaces to define Fermi structures of singularity, and these are completely dual. But the symmetry of one is broken, the other one's preserved, and we know that from the algebra it has to happen. And Zitterbewegung generally interprets as switching between them, but it's also an expression of the duality between these two spaces, neither of which is privileged. Both would be equally correct descriptions of the state and simultaneously valid, but we can only observe one of them. We could actually, I believe that we could actually switch it about, so which was broken and which wasn't. And possibly we could find a way of geometrically doing that. So I'm saying the intrinsically dualistic nature of the fermion requires the self-dual nilpotent form of quantum mechanics, which is based on the commutative combination of just two vector spaces, each dual to the other. Now, many people have wanted to found physics on space alone, and it's never quite worked. You can never quite package everything into just space, but I think you can package it into two spaces. It does seem to work if you structure it on two. Many other dualities emerge from the original one, and okay, that's what we've seen already, and that's the end. There's a little bit more about.
In terms of what you've just said, and in terms of the last sentence,
yeah.
I have a problem. The nilpotent formalism, of course, it's not of course to me, each single fermion sees all other fermions as constituting a vacuum,
I've already said
which is
that.
a mirror image of itself.
I've already said that many times.
But in fact, you've got zero totality producing a fermion and a vacuum which reflects that fermion, such that the totality is the vacuum.
Yes.
That's not what you've said there.
Yes,
It
but
sees all other fermions as constituting the vacuum.
that's correct. That's how it does the vacuum. Its interactions with all other fermions is vacuum.
But that's exactly what Dirac said.
Well, I'm not arguing with Dirac.
Okay, good. I thought this was new and revolutionary.
Well, it is. There are aspects of it. No, I mean, I'm not going to go against all physics just because I've got some new things to say. So Dirac does say that, but people have actually largely disregarded what Dirac said on that. I know that Dirac said that, and I know that Dirac had filled vacuum and all that kind of thing, but people ignore that to a large extent. They just say that's only of historical interest, but it isn't. It's actually physically true as well.
Didn't Feynman actually change that interpretation?
He may well have.
He did, but I think what we're talking about here is if we want to take what Peter says, we have to accept that when you've got a zero totality, that you create an electron, then you're actually creating also everything else,
yeah.
which is totality, which is zero minus the electron, which is something. But do carry on.
If you've only got one fermion from the fermion's point of view and all the other fermions are in vacuum, then do you not have one fermion and infinite anti-fermions?
No, because whatever's in vacuum is anti-fermion to that fermion. We'll see it as one anti-fermion. This is what happens with this representation. You can take an ensemble of fermions as a single fermion. You can make it behave as a single fermion. And so you can apply the nilpotent form to larger structures. This is something that I've done in other areas outside of physics.